Yeah. Okay, Shukai, go ahead.
Sounds good. Can everybody see my screen all right?
Yeah.
Um,
Sure.
okay, perfect. Um, well, thank you everyone for joining this internal kickoff meeting. I'm Shukai. I'm currently a fourth year at Professor Chen's lab. I'll now be sort of leading this with Hyukjae, my colleague Hyukjae and Haoran on this effort to kick off the second MagNet challenge. Um, so I guess for today, this is a organizing committee's kickoff meeting. So we'll sort of introduce I guess Professor Chen has already introduced everybody in this uh, in this committee. And we're also gonna talk about what is the new technical challenge that we're trying to propose for this next meeting, for this next competition. And then we're going to talk about a timeline, which is actually similar to Magnet Challenge 1. And please interrupt us as we go because we would like to collect feedback for our official kickoff meeting in a couple weeks. And then we'll make sure we finalize everything before APAC. And so for the public information session, which will kick off in 2 weeks, that's going to be hosted on a Wednesday, February 26th at 9 a.m. Eastern. We also have the registration link already. And in this, we'll hope that we can probably have some type of small scale public session information before we have the official kickoff at APAC here. And so far, within the organizing committee, we have me, Hyukjae, and Haoran, and Professor Chen from Princeton side. And then we also have Professor Charlie Sullivan, who is not able to attend today, and Thomas, who's a postdoc at Dartmouth. And we will be hosting this challenge too, just like the first one. And then we also have the judge committee, which will determine the winners of the challenge overall towards the end. And then we also have the liaison committee and advisory committee. And so thanks everybody for coming today. So rewind to Magnet Challenge 1, we actually had an extremely successful challenge where we had as many as 24 teams who participated at the end, many of which have proposed new ideas and published their ideas through a form of journals. And so after the challenge, we saw that the model accuracy and the models that people had developed within the Magnet Challenge have really pushed this frontier ahead in terms of improving Steinmetz equations or replacing the Steinmetz equations. And at the end, we had a summarizing paper, which included 133 co-authors, which is, I think, the largest number of co-authors within our community here, which was quite successful. And that sort of summarized the outcomes of what we were able to achieve within Magnet Challenge 1. And so for Magnet Challenge 1, we mainly focused on how do we replace the Steinmetz equation or improve based on that. And Steinmetz equation, as what we all know, essentially is an equation that helps you to calculate core loss and characterize the material's core loss specifically. And the teams sort of utilized the tools they had either through hybrid or machine learning methods to develop a model. In our case, for Magnet Challenge 1, some type of sequenced scalar prediction, and the scalar being the core loss here. But for Magnet Challenge 2, what we realized is that, well, challenge the first challenge is more or less finding something better than the Steinmetz. But challenge 2 is sort of asking, well, yes, we can do that for the Steinmetz equation, but to truly understand the behavior of a material, we should have some type of modeling framework that's able to depict the overall behavior in terms of hysteresis, not just core loss anymore. And so in a lot of cases, Magnet Challenge 1 is more or less a specific case, or rather say, compared to the model you would develop in Magnet Challenge 2, where in Magnet Challenge 2, we're sort of looking at, instead of a specific model, we're looking at some type of foundation model for magnetic materials. And within our scope of this foundation model, we have so far thought about, well, if you were to have a really good foundation model, then ideally this model should be frequency agnostic in any type of non-steady state excitations, where the model doesn't really need to see the frequency information in order to depict what is happening within the excitation cycle for the magnetic materials. And two, we also think that this model should be able to handle universal time step, as in it doesn't matter how long or short this time step is, and your model should be able to have accurate prediction regardless of how long or short it takes to reach the next point. And then we have the third one, which is sort of a hypothesis right now, which is the impact of our initial state on the overall behavior of magnetic materials using our models. So if you were to really have a good model, we think that regardless of what your initial state is, at some point, your model should be able to have this convergence over time to the material's steady state condition. And so these three are just the three things that we thought about could be the guiding factor to a good model for a very general framework for our MagNet Challenge 2 here. And so I don't know if anyone has any other inputs on what some of the other factors. But yeah, Professor Chen, you have something to say?
I guess generally what we're looking for is if we want to create a digital twin for magnetic material, we have to make it work for transient. And steady state is just one specific case of transient. And also in general, it should be converging, should be able to hopefully embed it into SPICE simulation. And in SPICE, we can select the time steps, whether it's in 1 nanoseconds or 1 microseconds. And the model should be general enough so that it's a same modeling framework and it can potentially work together with SPICE simulation. So that's why if we look at MagNet Challenge 1, it's more sort of like basic. Let's do something really basic, replacing statement equation. And MagNet Challenge 2, we really want to shoot high. We want to see if there's a better way to think about magnetics, either mathematically or physically or data-driven or a hybrid of math, physics, and neural networks. Is there a better way we can model the behavior of magnetics and how much computational cost we have to pay for that? Can we do it very efficiently so that ultimately we can put it into a SPICE engine? So that's sort of like the goal of MagNet Challenge 2.
Yes. Does anyone have any inputs or feedback on this?
Yeah, Oliver.
Yeah, maybe just a question to get it right. So if we consider like magnets as dynamic systems, which can have Markov properties, then normally we have a system which is represented by some kind of history. And if it's like really a Markov system, then normally if we transvert from state at some time k towards k+1, then the entire history doesn't matter, right? Because the entire information is saved into the new state at k+1. Right. So therefore, I'm maybe I don't get the main point about the hypothesis regarding the impact of initial state, because as soon as we have a state transition, the old state doesn't matter if it's a Markov system. And I think that's what we can pretty much assume about magnetic materials, right?
So usually magnetic material has this memory effect, right? What happened in the past, like we don't know how long it matters. For some material, permanent magnet lasts forever. For other materials, soft materials, it's lasts for shorter, and we don't know. It's a open question. How much history you need to know to predict the future? So you can't just infer based on the current state, because think about the BH loop. You know where you are at the BH loop. You also have to know where you were before to have a good prediction of what's happening next. So that's what we call it. But the hypothesis is that for soft material, it's a finite memory system. You don't have to remember forever to predict the future. But how long, we don't know. We hope the teams can help us figure out for different materials, maybe the memory we have to capture is longer or shorter. So that will be the answer to your question. So yes, it's a Markov chain system, but it has memory in there.
Okay, thank you.
Sounds good. So if you compare MagNet Challenge 1 with 2, you can see that, well, from a technical standpoint, yes, MagNet Challenge 1 is more looking at the steady state excitation waveforms that we already collected right through the MagNet database. And MagNet Challenge 2 requires us to look into non-periodic excitations or transient excitations. But you can also see it from a grand scheme of things, where Challenge 1 is more of people trying to compete within the track to see who's faster. And 2 is more of this exploratory territory where we open the track up. Now we're going from step 1 to step 2, are 2 different destinations, and there are many ways of getting there, right? So we really think that MagNet Challenge 2 will open it up to a much broader field for people to try to get to where we want to be. And why did we even think about having MagNet Challenge 2 in the first place? Well, what we do realize is that after MagNet Challenge 1, we did have a good way of sort of improving, replacing the Steinmetz equation. But overall, in most of the scenarios in applications or in industry, you don't really have always have steady state analysis to give you the specific core laws or whatever. And most of the times, right, that when you do simulations, you're going to go through transient simulations. And for some converters like the PFCs, you even have transient dynamics, right, over a periodic, some type of quasi-periodic wave excitations. And so we realized that there's still not a good method to really design magnetics in these type of transient conditions. And so if we don't have a good model for it, then for certain specific applications like the PFC, then you will just not have a precise design. Just like we talked about previously, even as a motivation for MagNet, you just don't have a precise design. Then we need to have unnecessary design margins that needs to cover for it. But as we shrink the size of our converters and our components these days, you don't really have the room for it anymore. So with that, designers may also have problems, right? If you don't have a good design and you have some type of design margins, you may not even be able to select the correct material for it. And so both of these plague our designs for magnetics these days. And so we realized that to have a good design as well as the material selection, you need to have a precise model, right? And so perhaps with this MagNet Challenge 2, we would have the opportunity to really design a good model and be able to shrink our magnetics by 20 to 50%, and perhaps every single AC/DC convert adapter can be 30% smaller, right? And so that is we're trying to reach for this goal, but I think this is quite a challenging problem, and so we really want people to come in and compete and see if we can even reach towards that goal. So if we want to have a precise model, then as we all know, we need to have very good high quality database. And so our original database with the steady state is no longer enough anymore, because most of the data we've collected previously for the 15 materials are precisely steady state excitations, and they are not really transient, right? And in a lot of cases, those data are still useful, but they are more or less the specific cases of what this model would be able to cover. So that means we will need new high quality data, and the data we have to collect actually has to be quite specific, and from the way we think about it. So when we want to have some type of a transient excitation, yes, we can create some excitation by changing a duty ratio, having some type of transient duty ratio step changes for every single switching cycle. But we also realize that if if we don't know where the B and H, from a data standpoint, if we don't know where the B and H start, and we would like to analyze the entire sequence, we sort of want the B and H on average out to be 0. And so we would still have to have some type of low frequency steady state to ensure that our sequence will start and end at the same point, right? And from a circuit perspective, that also makes sense to us in that when we have capacitors, right, DC blocking capacitors within our circuits, we would also ideally, from a circuit perspective, like to achieve charge balance. So we need to apply some sort of sequence in this rigorous way in which if we were to have step changes for the first half of our full cycle, we should have the negative duty ratio of for the second half so that we can actually achieve this low frequency steady state where our high frequency transient will be applied on top of this. And it does make sense in that if you look at a PFC, right, a PFC is also some type of high frequency transient on top of a low frequency dynamic here. And so this is essentially how we've decided to collect the data for our transient database here.
Yes.
And so yes.
So when we're talking about transient, we're not really talking about arbitrary transient because that places a lot of challenge in how do we define initial states and quantify the quality of the data. So within MagNet Challenge 2, when we talk about transient, it's actually a pseudo transient. It's like semi-transient with it's a combination of a low frequency and a high frequency and multiple frequencies together, but they are still a steady state in a wider time horizon. So that's what we call it as transient here, because it's challenging to do a real arbitrary transient because it's very hard to know where the initial states are.
So
that's correct.
So effectively, the excitation is high frequency superimposed on low frequency.
Correct. Yes.
That's right.
So more analogous to like the PFC application, which is it's steady state depending on what time horizon you're looking at.
Exactly.
Correct. Yes.
Okay.
So I would say there are room further to ask the question, what is the model for true transient? But that's not this year for now. We don't know how to do it yet.
Yeah. So you may see that each one of these sequence can be very long. You can have many duty ratio step changes, many combinations of step changes here within a full cycle. And I will talk about how long our cycles actually are for the MagNet challenge. But so far, we've collected data for, overall, we'll collect data for 15 materials. We so far have collected 10. Each material will have over 5,000 of such random duty ratio step change sequences across 7 subcycle frequency levels. And in this year, we're not going to do the frequency step changes, or we are more focused on the duty ratio step changes for each one of the fixed frequencies.
And we also the fixed frequency PFC. It's not like a variable frequency PFC.
Exactly. Yes. Mm-hmm. Yeah. And we also collected it for 3 different materials. And actually for each one of the sequence, we have 100 subcycles. So that's about 50 duty ratio step changes with the negative of half for the second half. So the sequence is actually quite long. So if you were to visualize this, one very important metrics we're focusing on for this year is that compared to MagNet Challenge 1, where we keep the overall time for each frequency overall time the same. And this year, we are keeping the sampling frequency for all of our sequences the same. And so what the importance of that is that since we're collecting it for 100 cycles for each one of these subcycle frequencies, and we want our models to be frequency agnostic, then perhaps it's in our best interest to not provide frequency information to the student teams, and so that it sort of helps them to have a model that can sort of self-identify without really having a frequency as an input, right? So to do this, if we have 100 cycles for each one of these subcycle frequencies, then we should sample them at the same with the same sampling frequency, such that your model within, let's say, if you look at a memories of 80 steps behind in the past, right? It should be able to see that 50 kilohertz should have a much longer, more linear trajectory than if you were to look at for 800 kilohertz data. And so that can sort of help the model to identify that. And so because we collected for 100 cycles for each frequency, that also means that each frequency will have different sequence length, overall sequence length. And we will basically provide because we're 7 sets of frequencies, we will provide 7 sets of BH pairs with the temperature information, but we are not going to provide them the specific frequency information for their purpose of just recognizing it within the model itself. And so that is one important thing that we have decided to do to ensure that hopefully we can push that foundation model to where it needs to be by already not providing that within our post-process data. And so far, this one material folder will include about 21 files, 7 sets, and we will do that for all 10 materials. So these are what we will provide for the student teams here.
Yeah, so basically what we're doing is we're taking pictures of the material every, I don't know, at 16 megahertz of sampling rate. And we don't tell them this is periodic or there's no periodic, there's no pattern in it. It's just a history of the material. And they can divide it into past and future and use a portion of it to train a model to forecast what's happening in the next few steps in the system. So that's what we're trying to do. And we will not give them frequency information, but we'll give them the time step, like how frequently we're taking these pictures. And also in order to make it like universal for potential simulation, they can also downsample it. Like for example, we sample at 1 nanosecond, but you can also downsample it to like 2 nanoseconds per data. And then that we can test the model's generality by asking the model to forecast the next step or next few steps. So that's why we set it in this way.
That's right. Yes. And so for training data we provide to them, we're just going to give them the data as is. They may do whatever they wish to do with the data. But I believe for testing, for our testing purpose, we will probably provide them with the same length for all of the sequences, so that we can have a uniform standard way of testing their models. So first, so essentially the outcome of this should be some type of callable function. And the students will receive 10 materials, I believe, by April 1st to train their models. And we will provide them with many BH pairs and with the information of temperature. And once they develop a good enough model, and they will turn in an initial submission, and then we will provide them with the 5 new materials, and they can further train with that. And for testing, then what's happening is then, given a long sequence, we are going to provide them essentially provided them with the past information, however long it needs to be, for B and H, BH pair. And then we're going to provide with the future B, but not future of H, which they will use to predict the outcome. And this may be applicable to have any type of sequence length for the past or for the future, as in we may have a very short past, but a long future, or we may have a very long past to predict the short future. And so any of these cases are applicable, which we'll determine towards the end of this year.
And honestly, we don't know. We don't know how much memory we need for each material. Actually,
Yeah.
It's actually a part of the challenge for the teams for a new material, how do they identify how much memory they have to read in their algorithm to predict the future?
Right.
It should be data driven as well. This part of the model.
That's right. So the overall strategies, right, to win the challenge for student teams is basically that its student teams should have a good understanding of the physics and the data, and their models should be reasonably explainable, hopefully. And they may use not only machine learning methods, but we also very much so encourage physics informed methods, or the hybrids of both, right? And the overall model at the end should have a good balance between the model generality and the model accuracy, right? The generality as in how can you apply it to different materials, and also different operating conditions, right? With a very small, compact, precise, very compact, simple model. And the hopefully these models can also be used to help manufacturers and provide perhaps implementations to software engineering, as in we believe that this MagNet Challenge 2 can really push us to help implement a good model into a SPICE simulation, for example, using Plex or LT SPICE, because if we are doing autoregressive forecasting, right, that's precisely what simulators really do. And that's one of the big motivations for why this is very potentially extremely useful for industry applications as well. And we also think that because now we've opened up our roads here, there are a lot of data scientists in the computer science areas who may have already done something similar for other applications. And we encourage the students to look out there and understand what has already been done, and perhaps also challenge what are the existing methods that are already done, perhaps they can improve upon. And so we really think that at the end of the day, our winning team structure does not really change from MagNet Challenge 1, where you do need experts from data science, software engineering, and experts in magnetics, as well as power electronics here. And we are also going to provide a tutorial to the student team sometime I believe in May. And this is just an example of what we have done so far, where we instead of predicting a sequence in the future, what we're doing is very basic, using the memories of the past 80 steps, which are arbitrarily chosen for a specific material, to forecast one step forward. To essentially, the initial goal was to have it such that it can be implemented into some type of SPICE simulators. And so for us, we're only predicting one point in future. So we have the BH pair coming into a neural network, and we're feeding in the next time step B into a projector, and then that's going to give us what is the H response for the next time step. And obviously, this is just one specific case. Does not need to be the teams do not need to rigorously follow what we have done, and we wish they can perhaps be innovative and look elsewhere as well to see what can be done to achieve similar capabilities. And so overall, the goal is that if you are given a very long sequence such as this, you can compare, and first you can compare and see that if you just use initial permeability to predict, you're going to be pretty much so very off, as we all expected, to what the measurements are going to be. And it's also not going to include saturation effects and all these. But the goal is perhaps we can have a model that can autoregressively forecast the future. And a problem that comes with it is the accumulation of error. So it depends on what models team are going to provide. It is expected that the prediction are not going to be as precise to the measurement as it can be. But so it is okay to see that there are going to be various performance behaviors amongst all the models. But the goal is that somehow the model should be able to predict either a point or a long sequence of data into the future. And this does not need to be what we do with machine learning does not need to be the only way. So far, one very close case to what we do is basically stock market forecasting, right? And obviously stock market forecasting has been done by many computer scientists in the fields already. And stock market essentially is more volatile and involves a lot more factors than what the magnetics do. So we believe that people should also look into other applications, such as weather forecasting, stock market prediction, to perhaps draw some inspiration on to perhaps get a model that can solve problems that are perhaps much simpler than what the stock market is doing. And so in this case specifically, you can perform different Fourier transforms and have different neural networks, perhaps one neural network model for some components and another neural network for different components, and then combine them at the end, right? Some tackles the big trend, some tackles the noises on top of the big trend. So you can do that way as well, but there's no limited methods as to how we can do this.
But we are still looking for smallest model. So ideally, this is a very simple problem. Like we know where we sit on a BH loop, and we just need that incremental permeability to know where we're going next step. So my intuitive way, or our intuitive understanding, is the simplest model should be very, very efficient. You shouldn't need like very complicated computational resources. But we hope that currently Shukai's model, I don't know how many parameters you have, like 1,000 parameters?
1,000. Yeah, 1,000
yeah,
parameters.
With 80 steps history, we need 1,000 parameters to get sort of like reasonably good results. But the 80 is like arbitrary chosen number, so that's like a few microseconds of memory. For ferrites, what we find for the particular material we are playing with, like a few microseconds of memory is enough. But maybe for different material, the length is different. And the model, ideal model probably should be scalable, so that if you are trying to model permanent magnet, you need a long history. If you're modeling soft magnet, you need a short history. And that's sort of our goodwill. We don't know whether at the end of next year, 1 year from now, we'll really see models like that. But who knows?
Yeah, well, ideally, you can just have infinitely long memory, but obviously, everything plays into a factor when you're training and with the current resources that we have. And so I think student teams can really seek to have opportunities to find out, well, what information are really needed, right? Do we need all the data from the past few microseconds, or do we just get specific data, perhaps the peak values, and to help you that has more higher impact on the future?
Right, but we hope to be efficient, because if we want to put it into SPICE simulation or combine this with finite element modeling, ultimately, then an efficient model will be particularly useful, even if it is less accurate.
Right. Yes. So, essentially, the information flow of MagNet Challenge 2 will go as follows. We will first provide the BH pair and data with temperature to the student teams, and the student teams can either choose equation-based, physics-based models, or to develop their own data-driven models, or even the hybrids. And at the end of it, we are also expecting some type of callable MATLAB or Python function like MagNet Challenge 1, which they'll first initially submit, and then they're going to test the data that the model has never seen before with the 5 new materials. And then we will evaluate their data based on model accuracy, the novelty, and as well as size this time as well. So overall flow does not deviate much from MagNet Challenge 1. So it should be familiar territory for most of us here. And so for evaluation, we essentially in this year, we're still looking at the model performance in terms of the 95% percentile error, as well as the RMS in the BH sequence. We also are thinking about perhaps also adding the core loss as another evaluation criteria for the model performance. And for model size, obviously we yearn for a much smaller, tiny, very efficient model. So I think model size also plays a big role in this year's challenge. And novelty, as usual, we wish the teams can think out of the box and have it does not need to be the best model, but we also want teams to be innovative. And this year, the generality, in addition to being able to apply to different materials, operating conditions can also be very generalized. And so the model should be able to cover a wide range of operating conditions without specific inputs for the model. And the final winners will be selected by the judge committee here, which are 5 of our professors here. Thank you for coming again. So that will be happen, I believe, earlier next year.
Right. So let's pause here. Maybe let's
Sure.
Any technical question, anything we didn't thought carefully, or anything that is confusing or may create problem. We don't want to run the challenge in a half and then student team reported a technical problem and we feel like, oh, we don't know how to do it. And this year is more risky. Like last year, we feel like everything's sort of in control. And this year, the challenge is like, we don't, like even us, we don't feel we have deeper enough understanding about it yet. But we do have data.
What's the timeline? We're launching in APEC, and then when is the challenge over?
So we're launching APEC, and then we're gonna announce around next year's APEC the winners.
Go ahead.
Submissions due at Christmas, though.
So
Yes.
this is what we're gonna do. The big timeline is April. We'll release all the data. So we'll do our check and then check the quality and things like that. And then the student team has until November to play with the training data. They can do whatever they want. They can separate the training data as training for model and testing themselves. So that's for 10 material. So they will play with 10 material for half a year, for 6 months. And then starting from November, we'll release the data for the 5 material, which is for final competition. The 5 material, a big portion of the 5 materials data will be released for training, and they can use it to fine tune their model, improve their model, which was trained by other materials data. And we'll keep a small amount of that data for that 5 material for testing. And the testing will be again segmented in a way that we just mentioned. It will be separated into past and future, and ask them to predict the future, and we compare the accuracy for the future. So that's the general timeline. About 6 months of training and 2 months for final testing. Any other technical related comments?
I've got a question, Minji. And I think I need to review the materials more carefully, but just to clarify, the transient waveforms we're looking at are all PFC-esque type of waveforms.
Yes, we're not
Okay.
we haven't figured out a way to define true arbitrary. So we define this year's transient as like pseudo transient. It's like combining a low frequency envelope with a high frequency switching pattern. So the student teams may choose. I can imagine one strategy is to separate the low frequency and high frequency and predict the trends, and also embed or superposition. But superposition is not good strategy for magnets, we know. So we don't know what would be the best way. So I would say we call it transient, but this year it's not true transient. It's like PFC type of transient.
That might just help in the messaging, so students maybe are more encouraged to take it on, right? If it's pure transient, people get scared or maybe intimidated, and also it opens up that future competitions could deal with different transients.
Yes, right, correct, yes.
And this paper at the bottom is, it has the details of how you measured this data, is that right?
Yes, it's it's in APEC.
Got it, thanks.
Yep.
Yeah, sounds interesting.
Do you know which day it's being presented at APEC offhand?
Not sure.
Right,
we can
okay.
figure it out. We'll figure it out and send it to you guys. We'll send a follow-up email after this meeting with the registration link for both the public online announcement and the APEC. The APEC launch events will be on Wednesday. So Wednesday APEC afternoon, there'll be an in-person launch event. Yeah. So I guess the most confusing part is the time step. Like, why do we have different length for different frequency? It's because we are sampling at the fixed time step. So for the low frequency, it's longer. You need more cycles to more sampling to cover 100 cycle, and for higher frequencies, it's shorter. But for the student teams, they don't need to know that. We may just separate the long sequence into many smaller, shorter sequences, and don't tell them the frequency. So from their side, it would just be time steps of past for a variable length.
But they'll know, for example, that the ferrites were not gapped when the measurements were taken. That kind of thing will be available to them.
Yes, so we probably should mention it's all toroidal core. It's all in similar dimension. Yeah.
So basically, the shift is from challenge 1 to challenge 2 is to look at new methods to predict the minor loops.
Yeah, you can think about it
From-
in that way. It doesn't even need to be a minor loop. It's just that next step. It's like driving a car. You know what's past in the future. Where's the next step? Just that one step.
Okay.
Depending on what
Right.
happened. And of course, error can accumulate. If you make small error every step, then after a long time, your predictions go off. Okay, yeah, go ahead. Okay.
Sure. So for the student team eligibility, it will be exactly the same as MagNet Challenge 1, where we'll have minimum 5 student team minimum 3 student team members, right? And then the maximum will be 5. And each team will need to have 1 or 2 undergrads or between 2 and 3 grad students. And we have to have at least 1 faculty advisor and optionally 1 industry mentor.
So we are very flexible. I think in our impact last year, we pretty much admit all the teams. So we just encourage, all of these are just encouraging them to be a mix of undergrad and grad, but they don't have to strictly follow the rule. And also based on last year's experience, we don't really have conflict of interest. So everyone here can lead a team except Princeton and Dartmouth, because we created data, we can't participate. But other than that, I don't see any conflict of interest because it's just open information. And everyone, if you have students, please encourage them, and you can still be the advisor of the teams because our rules are all transparent and open. There's no conflict of interest.
Right. Yeah. And back to where what the question Alex asked earlier on, essentially this is our timeline. And I believe once they finish submission, we will spend about a month or 2 testing and discussing with the judge committee to select the final winner. And other than that, I believe we will probably have a tutorial session sometime in May, right?
Or throughout the summer, maybe a few.
Right, all throughout the summer, right?
How many tutorials we can develop? So we will try to sort of fill up the summertime so that they can play, and hopefully they can. This year we have previous teams, so some of the teams may even be ahead of us. So we'll see. Maybe they can offer some tutorials. So we'll see. We'll try to keep the summer busy.
Yes. And so finally is the money. I guess we will probably have something similar or even more than last year's prize money, right? So
last year we have 55K, and this year hopefully we can have more than 60K total prize. We're still talking to companies like NVIDIA, TSMC, and TI. So I'm pretty confident we can get more money than last year. So. Thanks for everyone.
So, yep, that's overall. That's it. Yeah, thank you for
and intellectual property. If the student team has to file a patent or do anything, they should do it before they submit anything.
Yep. So that is
all. Can you send over the full slide deck? Is that okay?
Yes.
Yeah.
We'll send
I apologize for being late.
Yeah. Thanks, Dave. Yeah, we'll send the slides, and we'll together with the registration link for the 2 events which are upcoming. So you don't have to be there. We highly appreciate you be here, but if you have any comments, let us know, and we'll post everything on GitHub. So the recording of the meeting will be on GitHub. We hope to minimize our utilization of your time throughout this process. So we hope you to be engaged with us and provide any feedback, but you don't have to have to show up in any of the future meeting, except for the judge committee. You guys have to show up for judging the competition. Wilma.
Yeah. So yeah, thanks a lot, Minnie and Shukan, really for the presentation. I don't know if I missed it, but I just wonder about the materials. So you mentioned indeed model for magnetic materials, and you mentioned also this database of, was it 50 materials? Are the groups restricted to those 50 materials, or are other materials also possible there? I'm just thinking in, for instance, if we involved industrial partners, as you mentioned, that it should be there. Perhaps they could be interested also bringing their own models to the competition and see. But I don't know how easy
So
is
I think
to
I think
have
for
a common ground for models there and to evaluate them. Yeah.
right. So we'll offer 10 material for the training.
Well,
And
10.
that training process from April to November, basically student teams can do whatever they want. If they have their private data, they can even test their model on their private data. We don't care.
Yeah.
We just offer 10 material for teams who don't have any data to play with, but that's not restricting to anything. For the testing, which will happen from November, that's where we'll be restricting to that file material. And that file material will be kept confidential. They don't even know the name of the material. So this is just file material A, B, C, D, E. And that has to be kept universal, right? Everyone has to be testing on the same material for the
Okay.
challenge. For the challenge.
Yeah.
But if you want to publish a paper or write your thesis, like of course you can do whatever you want. So
Yeah. Okay, understood. Thank you.
So in the end, one way of thinking about it is we're basically defining a game, and we'll make it clear that the winning model may not be the best science, and the best science may not be the winning model. So again, so the winning model just means that it work well for this file material, but it may not be the best model exists, or there always better way to make things better.
So Minji, is the objective to train the model on some materials, but then try to use the same model to predict the behavior of a different material?
They can think in this way, but they don't have to. Because that's actually a philosophical question we ask ourselves. Like, do we think we have to use one universal framework to model all ferrites, or we should look at the data first, and some ferrite should be modeled in this way, and other ferrite should be modeled in other way. So we don't restrict that here.
I guess if the testing data if the material of the testing data is not disclosed, then you are kind of asking people to have a universal model.
No, the disclose, just like we don't disclose the name, we give them new training data for the new material.
Right, but their model has to be able to tackle it without knowing what it is.
They don't have to know. For example, for the training, we just give them N87. For example, we tell them the manufacturer name of the material. For the final, we don't tell them which manufacturer it is, because if we tell them,
that's
they
what I'm saying.
Buy the material and get new data, and that creates some fairness problem. Like other teams may not access to the material. So that's the purpose of keeping the name of the material confidential, but we're not forcing them to use what they know from the 10 material to build a new model for the 5. If they find it beneficial, they can do it. If they develop a model which doesn't need cross-material shared information, we are open to that. I think that may be a better strategy even.
Okay.
But yeah, good question. I think we probably want to clarify the purpose of keeping the name confidential for the test model is just for that everyone is training based on the same data. Although this comes to a problem like how is the data quality? how accurate is the data, and that's something which is beyond the challenge. We should think about the challenge as a challenge, and the model which works well for the data we offer, ultimately, hopefully, will also work well for the data which the manufacturers eventually offer in the future. But that's our hope. Any other question? Comments? I think we're good. Again, I guess everyone needs some time to digest the material and think about it carefully. We are very excited about the challenge, and technically we're very interested. I think this year is really a true challenge because we don't know, honestly. So if you want to set up a meeting with us, feel free to reach out to us and we can chat with the extended technical discussion. Other than that, thanks everyone for your time. We will start promoting and share. We'll probably keep quiet for a couple of days. If you have any feedback, let us know. Otherwise, then we will sort of gradually ramp up our publicity, and you'll see it on LinkedIn and social media and emails. Oh, we're going to have a MagNet challenge too in the next few weeks.
Excellent.
Great.
Yep.
Thanks, Minji.
Yeah,
Great.
and
Thank you
other
very
thing,
much. Well done.
right, go ahead. One last thing is is for the judge committee. We don't have to finalize how do we evaluate the rule until November, but it's good to, if you have any thoughts, we can have a discussion within the judge committee. How do we compare across different models, and how do we weight the novelty and model size and accuracy and so on. Okay. All right. Thanks, everyone.
We can see the
Thanks.
results first before we make final judgment.
Yes. Yeah. We'll learn more throughout the process, and then once we start to create the tutorials, and you can see the tutorials, you will get a better feeling of how things look like. Yeah. Okay. All right.
Thank you very much.
Bye-bye.
Thank you very much.
Cheers.
Thanks.
Thank
Bye.
you.
Thank you.
Good night.
Thanks.
Bye.
Bye.
Yeah.
Mhm.
Thanks, Dave.